In this video, we solve problem 6 of Unit 13. In this problem, we have a simple circuit provided by a real battery here, which has its ideal part and also its resistor. And then we have it connected. This is the positive side of the battery, so the electric current is going to flow in this sense. So we have it connected to this here, that is a switch. So if the switch is open, the current cannot flow because there is no continuity. And if the switch is closed, the current can flow. And then this is a resistor here. Then we have an ammeter. And then the circuit closes. And we are measuring the potential difference across the real battery with this voltmeter here. Okay, so we're going to consider both the voltmeter and the ammeter as ideal, so they're not going to alter in any way the circuit. Okay, so the first thing is that when we have opened the switch, the voltmeter that is measuring the difference of potential between the sides of the battery is saying that there is 3.08 volts. And when the switch is closed, when this switch closes and there is current flowing through the battery and also through the rest of the circuit, the voltmeter says that the potential difference is 2.97 volts. Okay. And when it's closed, we have an intensity, electric current of 1.65 ampere. So the first question is, what is the electromotive force of the battery? And this is you have to remember from the theory that if we draw here the potential difference across the battery and here the electric current flowing through it, if the battery was ideal, then this would not change. This potential difference would be constant independently of the amount of electric current flowing through the battery. However, in real ones, we have that this is decreasing, and this we can represent this by saying that the potential difference across the battery is equal to the part coming from the ideal part of the battery minus the intensity times the resistance of the small resistor. Okay, so what happens when the circuit has the switch open? When the circuit has the switch open, when the switch is open, this means that the intensity is 0. So what we are measuring is with the switch open is that this difference of difference of potential is going to be equal to the electromotive force. So the electromotive force has to be 3.08 volts. Okay, because it's the potential difference that the battery, the real battery, is providing when there is no electric current flowing through the battery. The next question they ask is the value of the internal resistance. This is this small r. So that is easy to solve, because when the switch is open, then we have that V is equal to epsilon minus I times R. So from here we can say that R has to be equal to epsilon minus the real difference of potential between the sides of the battery divided by the current that is flowing. So in this case, this small r is equal to 3.08 minus the reading of the voltmeter, which is 2.97. So this is 2.97 volts divided by the electric current, which is 1.65 ampere. So if you calculate this, you would get that this is equal to 0.067 ohm. Okay. And in the third part, they are asking what is the value of the resistance of this resistor here. And that is easy to solve applying Ohm's law when the switch is sorry, this should be closed. When the switch is closed, because the potential drop across the resistance is equal to the amount of different the potential difference that the voltmeter is reading. So by applying Ohm's law, this is the resistance is V divided by the electric current. So this is going to be 2.97 volts divided by 65 ampere, which is just 1.8 ohm.